A team of researchers from the University of Toronto's Faculty of Applied Science and Engineering has leveraged quantum mechanics to optimize the active layer within a device known as an inverted perovskite solar cell, a technology that could one day result in mass-market solar cells that a fraction of those currently on the market. At present, virtually all commercial solar cells are made from high-purity silicon, which takes significant energy to produce. But researchers around the world are experimenting with alternative solar technologies that could be manufactured and installed with less energy and at lower cost. One of these alternatives is known as perovskite. The power of perovskite materials comes from their unique crystal structure, which enables them to absorb light in a very thin layer and convert it into electricity efficiently. A new research paper related to perovskite solar cells is published in the journal Nature Photonics. One of the authors of the paper says that perovskite crystals are made from a liquid ink and coated onto surfaces using technology that is already well established in industry, such as roll-to-roll printing. Because of this, perovskite solar cells have the potential to be mass-produced at much lower energy cost than silicon. The challenge is that right now perovskite solar cells lag traditional silicon cells in stability. In this study, the researchers aimed to close that gap. The researchers are using a strategy based on an inverted solar cell structure. In most prototype perovskite solar cells, electrons exit through a negative electrode at the bottom layer of the cell, with the holes they leave behind exiting through a positive electrode at the top. Reversing this arrangement enables the use of alternate manufacturing techniques, and past research has shown that these can improve the stability of the perovskite layer. But the change comes at a cost in terms of performance. It is hard to get good contact between the perovskite layer and the top electrode. To solve this, researchers typically insert a passivation layer made of organic molecules. That works really well in the traditional orientation because holes can go right through this passivation layer. But electrons are blocked by this layer. So when you invert the cell, it becomes a big problem. The team overcame this limitation by taking advantage of quantum mechanics, the physical principle that states the behavior of materials at very small length scales is different from what is observed at larger ones. The researchers say that in their prototype solar cells, the perovskites are confined to an extremely thin layer, only 1 to 3 crystals in height. This two-dimensional shape enables the researchers to access properties associated with quantum mechanics. They can control, for example, what wavelengths of light the perovskites absorb or how electrons move within the layer. The team first used a chemical technique established by other groups to produce a two-dimensional perovskite surface atop their solar cell. This enabled the perovskite layer to achieve passivation on its own, eliminating the need for the organic layer altogether. To overcome the electron blocking effect, the team increased the thickness of the perovskite layer from 1 crystal in height to 3. Computer simulations had shown that this change would alter the energy landscape sufficiently to enable electrons to escape into an external circuit, a prediction that was borne out in the lab. The power conversion efficiency of the team's cell was measured at 23.9%, a level that did not fade after 1000 hours of operation at room temperature. Even when subjected to an industry standard accelerated aging process at temperatures up to 65 degrees Celsius, the performance only decreased by 8% after more than 500 hours of use. Future work will focus on further increasing the stability of the cells, including under even higher temperatures. The team would also like to build cells with a larger surface area, as the current cells are only about 5 square millimeters in size. Still, the current results bode well for the future of this alternative solar technology. In their paper, the researchers compared their prototypes to both traditional and inverted perovskite solar cells that have been recently published in the scientific literature. The researcher says that the combination of high stability and high efficiency they achieved really stands out. Perovskite technology is only a couple of decades old, whereas silicon has been worked on for 70 years. The researcher says that there are a lot of improvements still to come.